Today we want to continue looking at this old problem. This is an old problem in projectile motion where we have an object launched from an initial height of 30 meters with an initial upward velocity of 10 meters per second. And we know we're going to have some parabola showing the height as a function of time. What we want to incorporate into this old problem is how derivatives and integrals can show up in this problem. All right. Let's first talk about the standard operating problems, standard operating procedures that go along with this kind of problem. Typical kinds of things that we ask for when we present you with this kind of problem are: when is the maximum height achieved, and how high is the object at that time? So one of the questions that might show up is: when is the maximum height attained, and what is that maximum height? Now, from a pre-calculus standpoint, this is a question about a parabola. We want to find the vertex of the parabola. That's the old version of the problem. So before calculus, not necessarily pre-calculus the class, because kind of all calculus is all class before this one were pre-calculus. So you could be all fancy. It's like, oh yeah, I was in pre-calculus when I was in fourth grade, because it was before calculus. So from a calculus, pre-calculus standpoint, we're thinking, what is the vertex? So another way to ask is, what this question is asking is, what is the vertex of this parabola? So we just have to find the vertex of the parabola. Well, let's just do that. So one way we could do this is, one way that this is done is we just know that the vertex, the x coordinate of the vertex is the opposite of b over 2a. So if we take this 10 and divide it by 9.8, we get 1.02 approximately. And then to figure out k, we just take this and plug it into our function. So we rewrite the function in its vertex form. We do that by either remembering that h is the opposite of b over 2a, or we complete the square, in which case we find that h is the opposite of b over 2a. So this would be a shortcut to just completing the square. That's all we're really doing here. But from a calculus standpoint, we know that we're looking for a local maximum of the function, which means we want to take the derivative, set it equal to 0, and solve. So an alternate way of asking this question, of framing this question, is find a local maximum of our position function. So another way to think about this I should answer the question. So the object reaches a maximum height of 35.1 meters at 1.02 seconds after being thrown. All we needed to do was find the vertex of a parabola. That's a zeroth derivative method for solving this problem. Find the vertex of the parabola, we complete the square, find the vertex, done. Interpret the answer. But we can also answer this question. We can also frame this question in terms of calculus with the things that we know now. So another way to think about this question is to think about finding a local maximum or a global maximum of the function, finding a maximum. And that is taking the derivative, set it equal to 0, and solve. So the problem changes in how we think about it. Rather than just thinking of the function, we think about taking the derivative, setting it equal to 0, and then solving. So we're going to solve s prime of t equals 0. This will give us a critical point, and then we can classify that critical point as a local maximum, a local minimum, or neither of those. We know it's going to be a local maximum because we know we're dealing with a parabola. So s prime of t is v of t. We're going to set this equal to 0 and then solve. So we found a critical point, and we need to classify it as a local minimum, a local maximum, or neither of these. Now we have three functions. We have three derivatives that will help us classify the critical points. The original function, the 0th derivative, the first derivative, and the second derivative. Based on the 0th derivative, based on the function itself, since we know that this is a parabola, this must be where the vertex is, and since the leading coefficient of the parabola is negative, this must be a local maximum. So we can classify using what we know about the function itself. Since s of t is a parabola with a negative leading coefficient, this point is at the vertex. Since S is a parabola with a negative leading coefficient, the vertex is the highest point. And we say that the object reaches a maximum height of 35 point, we just plug that in, a maximum height of 35.1 meters at 1.02 seconds after being thrown. So we come to the same conclusion. Happens at 1.02 seconds. And we have previously calculated that this is going to be 35.1 meters. We can classify this critical point using the first derivative. The critical point is the time when the velocity is zero. And that means it's a time when the velocity is possibly changing direction. Velocity is 0 meters per second at 1.02 meters per at 1.02 seconds. So we can just check what's going on before that and what's going on after that. Oops, not T. So now we can pick a value before 1.02 and see which direction, what sign of the velocity is. So 0 is fun to plug in. When we plug in 0, we get negative 9.8. So V of 0 is negative 9.8 times 0 plus 10 meters per second. More importantly, the velocity is positive. The object is going up. And then we pick something after 1.02, like 10. And ZV of 10 is negative 9.8 times 10 plus 10. Negative 98 plus 10 is negative 88 meters per second. And so that is down. So after this, the velocity is negative. So the object is going down. So at that critical point, the direction has changed from up to down. So therefore, it's a local maximum. We can also classify, oh, go ahead. Yes, because that's how we found the 1.02. We took the derivative, set it equal to 0, and then solved that. So that's when the velocity is equal to 0. So the critical points happen when the first derivative is equal to 0 or when the first derivative is undefined, which is not something that's going to happen with these polynomials. That's the only place that we have a chance to have a change in direction. And so we just needed to verify that we changed direction at that point. Thirdly, we could classify our critical point using the second derivative. The acceleration is negative because we decided up is positive and down is negative. Second derivative is negative, which means the function is concave down, which means we must have a local maximum. We have a function that is flat at 1.02 and concave down at 1.02. That means we're dealing with a local maximum. And it's all crammed into the bottom of the page. And all this space up here means I'm bad at planning out what the page is going to look like. The reason that we classified this critical point that we already knew was going to be a local maximum just because of the geometry of the problem. Stuff goes up, stuff goes down. That wasn't the point of the problem. The point of the exercise was not to find out the 1.2 and the 35.1. We had that before, just based on the function. We knew that years ago, back when we first started learning about parabolas and what we could use parabolas. That wasn't the point. The point was to see how calculus applies to something that we are familiar with. When you learn a new thing about math, that might apply to an old thing, it's really important that you resolve those two. You take the new technique and apply it to a problem that to which you already have the answer to see how the new technique works. Here, the thinking was, let's figure out when the velocity of the object was 0. Because that would be when the object is changing direction. It has positive velocities, then at some point it has no velocity because it's changing direction, and then it switches to negative velocity. Any questions? How's that okay? Everybody looks mad. Sorry I was late. Or was I so late that should I say, sorry that I showed up? So like, oh, dude, I was about to leave and then you showed up and now I'm stuck here. You're totally not stuck here. Like you can just like get up and go if you want to. That's like an option. Y'all are adults. You know what I mean? Like like in high school, you get in trouble for that. Like you just straight up got up and walked out of class and didn't come back, like grabbed your stuff and walked out of class. In high school, they're like, hey, where are you going? Right? But here, you just go. Like if you have somewhere to be, you know what I mean? It's weird. Sometimes it's a culture shock. I can see which students are straight out of high school because the first time someone does that without like asking, or maybe they asked beforehand and you didn't see it happen, like someone just like packed up their stuff and then like walk out the classroom. Like you see all the students that are fresh out of high school and then it's funny because then they try it. They're like, I'm not stopping them at all. I just keep doing what I'm doing. You know what I mean? The funding model is different. Like you miss a day in high school, and the school gets less money. So rather than going to the people and saying, this funding model is kind of dumb, and it makes people do dumb things, they turn that and blame you because you have no power in the situation. So that the easiest people to blame are the ones that have no power in the situation. You know what I mean? That's a common theme, by the way. The other thing that we want to be able to interpret is some definite integrals. Yesterday, we saw the integral from 0 to 3. When we integrate a derivative, that's going to tell us how much the function changed. So we want to be able to interpret the definite integral as well. So recall, one of the reframes that we had for the fundamental theorem of calculus was to say that the definite integral from a to b of f prime of x is f at b minus f at a. The definite integral of a rate of change of a function on an interval is how much the function changes on that interval. So this is the definite integral. The definite integral of the rate of change of a function on an interval is the change in the function over that or on that interval. The definite integral of the rate of change of a function on an interval is the change in the function on that interval. So when we integrate the velocity, we find the change in height. So if we take this example that we're working with, if we look at negative 9.8 t plus 10, that's our first derivative. That's our v of t, or our s prime. Integrating from 0 to 1.2, 1.02 will tell us how much the height changed in that time. So just fitting it into the fundamental theorem of calculus, it's going to be s of 1.02 minus s of 0. Oh, I'll have to write down. Or I did it. Since we already know so much about this function, we know that it started off at a height of 30, and after 1.02 seconds, it reached its maximum height of 35.1. So note that this is not the height at 1.02 seconds. This is the change in height from 0 to 1.02 seconds. Not the height, but the change in height. Specifically the 1.02 seconds from 0 to 1.02. Questions? We know that at a certain point, if we're standing on this 30-meter tower, I just realized how tall I made this initial height. And how hard we didn't throw this thing upward. That's fine. We might want to know, when does it pass? We know it starts at 30, it goes up to 35.1. At a certain point, it's going to be back down to 30 again before it continues on down towards the ground. So we might want to think, when does that happen? Because we know, based on symmetry, based on the physics of the problem, we know that that's going to happen again. Based on the physics of the problem, we know that this is going to happen again. So we might want to know, when is the object back to a 30-meter height? Based on what we know about the function, our function is a parabola, and our parabola is symmetric about the vertex. About a vertical line through the vertex. It took 1.02 seconds to get from our starting height to our maximum height. So it'll take 1.02 seconds to get from our maximum height back to where we started. So it'll be 1.02 seconds from the maximum height back to the start. So that'll happen at 2.04 seconds. We can check this. Let's check. $30.00816. So that's 30. So it checks out. We use the symmetry. We took what we knew about parabolas. We know they're symmetric, about a vertical line through the vertex. So if the y-coordinates are the same, when the y-coordinates are the same, we are evenly spaced about the axis of symmetry. If this is 1.02 from the middle to the left, then it is also 1.02 from the middle to the right. That 1.02 on the left and the right, that is the plus or minus. If you're thinking of the quadratic formula, that's where the plus or minus shows up. There's the middle at the vertex, and it's plus or minus. Fortunately, we don't have to do that. We can also use the function, our parabola. I'm saying, when is this equal to 30? And we can just solve an equation. So if we subtract 30, we're just trying to solve negative 4.9 t squared plus 9.8t is equal to 0. Subtract 30 from both sides. And then factor. If I factor a negative 4.9 t square or t out. Yeah, I don't want to do it that way. Let's just factor a t out, and that'll leave a negative 4.9 t plus 9.8. So t equals 0 from this one. We knew that one already because that was our starting height. And the negative 4.9 t plus 9.8 equals 0. So t is 9.8 divided by 4.9, which is 2.04. So this 30-meter height happens at 0 seconds and 2.04 seconds. So we can do it mechanically, ignoring all the wonderful symmetry that we have because we know this is a parabola, and we can just mechanically force S of t to equal 30. We got to find out who's thinking about the problem and who's following their program. I mean, training. We're not supposed to call it program. Any questions? I'm not saying we programmed you when you were children, but we kind of programmed you when you were children. We can also think about this. We can also think about this in terms of the velocity. That would require a little more physics, but our initial velocity was 10 going up. When is our velocity going to be 10 going down? So we could also use the velocity. I can figure out when the velocity is -10, the opposite of our starting velocity. And we can see here where the 2.04 is going to show up again. That original 1.02 came from 10 divided by 9.8. And now we're just going to be doing 20 divided by 9.8. Questions? One last thing, thinking about definite integrals. I wanted to interpret definite integrals more. Now I got to sidetrack. Another thing to think about in terms of definite integrals, if I integrate this function from, if I integrate the velocity from 0 to 2.04, what am I going to get? Just thinking in terms of definite integrals. If we integrate from 0 to 2.04, this velocity, what's this going to equal? So we're integrating the rate of change on an interval from 0 to 2.04, and that will represent how much the height has changed from 0 to 2.04. How much has the height changed on this 2.04 second interval after being thrown? If by your silence it means it hadn't, because 2.04 is when it's back to 30, then you are correct. We integrate this function from 0 to 2.04. We are back to the original height. That's when we found out 2.04 seconds is when the ball is back at 30 feet but headed down this time. So the total displacement is 0. The distance that it's traveled is a different question. It's gone 5.1 meters up and then 5.1 meters down. So we would say it's traveled 10.2 meters, but the definite integral cancels out direction. So like if I integrate my speed from this side of the board to this side of the board and then this side of the board, my distance traveled is going to be about 16 feet, but my integral from 0 to however long it took me to get back is going to be 0 because I started and ended at the same place. So that's displacement, is how far my position has changed, versus distance, how far I went. Any questions? Comments? Snide remarks? How's everybody okay? Everybody looks so disgruntled. You're giving me disgruntled. What? It's because we're dealing with the problem that we solved before the class even started, and I still kept talking about it. But getting to the answer is never the point in your math class. You know what I mean? Always remember that getting to the answer is not the point. You just want to get to the answer, you just be hiring me to do your homework for you. If you can't afford that. Any questions? Comments? All right, that's going to do it for today. That's going to do it for this week. I will see you all on Monday. Everybody have a good day. Everybody have a good weekend. And thanks for playing.